Good afternoon again. So my name is Ozgur Yazaydin. Not Alberto Australia, but this course was actually taught by Alberto a year ago. But then he left UCL for Oklahoma. Okay, he's currently in the US. But these are slides from a course that we taught together. He used to teach the first half mostly theoretical, fundamentals, and I'm still teaching without Alberto the second part, which is more practical. So so all the credit actually in terms of material goes to Alberto. I'm going to try to narrate his slides. Okay, so hopefully I'll do my best and try to answer your questions. But in the second half, what I would like to do is, so after we cover this intermolecular forces part, what I would like to do is to give some examples from my current research about how we fit force fields, okay, with respect to fluid phase equilibrium data. Okay, so that will come after we finish this this first topic. After which I think I'll give a break, and then as I said, this in the second part, we'll talk about fitting force fields with respect to phase equilibrium data, vapor liquid equilibrium data. I'm trying to use two monitors here. Okay, so just give me a moment while I'm setting up a few things, because right. Okay, super. Right. So yes. So in the first part, there's going to be a couple of parts in this hour. Okay. So we'll talk about the first part will be dedicated to generalities and then electrostatic forces. Okay. So let's get started. In general, okay, intermolecular forces in general, these are models, approximate models that helps us to model systems at the molecular level. Okay, a model is as good as it's as good as it's capable of predicting experimental data. There's no model that literally works perfectly. Okay, I mean, for instance, for water, I think there are 50 different molecular models around, and some of them predict certain properties best, but then that do not do a good job in predicting other physical parameters. Okay, so but then they're very useful in terms of molecular simulations. When I'm saying molecular simulations, I'm talking about force field based or classical molecular simulations. They're extremely useful for predicting several properties. For instance, the phase equilibrium properties of fluids. Okay, vapor liquid equilibria, predicting like boiling points, critical parameters, as I'm going to illustrate in the second hour, but also helps us to, for instance, predict the amount of gas absorbed by a porous material. Okay, again, they all have their limitations, but as a personal philosophy, I always try to give this message that a modeler's job is not simply to try to reproduce experimental data. Okay, yes, there is value in matching experimental data, but actually our job is to guide experimentals, okay, in the right direction. So and in that sense, the molecular modeling has come to a state that most of the predictions are quite accurate, right? But as long as you're very careful with the models that you set up, right? Okay. Right, yes. So this symbol stands for potential. So there you have two particles and separated by a distance of r. So this is the potential, and then this is the force. I think most of the people here are physicists. So the potential energy is nothing but the minus derivative of the force is nothing but the derivative of the potential with respect to distance. Okay. By convention, when we have forces greater than 0, that indicates repulsion between two particles, and then when the forces are negative, this indicates attraction. Now, when the potential, okay, is at the minimum, that means the force is at 0. Okay, and then so force at 0, yes. And same thing for the maximum, where the potential is at its maximum. You can see the force is at 0. You would have these inflection points, okay? And then at these points, the force tends to be either at minimum or maximum. Again, there's another inflection point here, okay? And then the force reaches to its maximum. Now, for molecules would like to be obviously at the global minima, but this is not always the case. Sometimes they're stuck in these local minima, and then they may actually get stuck here for a very long time to go from this point to the other point, okay? And for them to, for instance, to move from local minima, the global minima to another minima, or from any minima to another minimum, an event must happen so that the particle can overcome this potential energy barrier, so that it is relocated from this minimum to the other one. Okay, right. Speaking of condensed phases, the attractive forces are mostly responsible for the properties of condensed phases. So, for instance, two examples that we can discuss here: energy of vaporization, okay, and specific heat of a gas at low pressure. Okay, so for instance, sorry. Okay. So, for instance, if the attractive forces between two molecules they're strong, then this fluid would like to be in the liquid phase, because the attractive forces kind of tends to bring them from the gas phase to the liquid phase. Okay, but on the other hand, for instance, think about the specific heat of a gas at low pressure, and the key word here is the low pressure. Right now, at low pressure, the particles are going to be away from each other. Right. So what is the definition of the specific heat? It's the energy required to increase the temperature of a substance by 1 degree. Now, the heat that you give, right, because the particles are very away from each other, right, the heat that you give is going to go into the vibrational modes of the molecule, and it has nothing to do with the intermolecular interactions. Whereas, as I said, in the case of, for instance, a liquid, think about the fluid which is in vapor-liquid equilibrium. Like, you have the gas phase in equilibrium with the liquid phase. Okay, the attractive forces, okay, right, will I don't want to use the word force, but okay, we'll force them to go to the if there's strong attraction between molecules in the gas phase, they would like to be in then they would like to go into the liquid phase. Okay, right. So the configuration properties are those that depend on interaction between molecules rather than on the properties of isolated molecules. So in that sense, the heat of vaporization, that's a configurational property. But then specific heat of a gas at low pressure, this is not a configurational property because of the separation between the gas molecules. Now, if we, for instance, increase the pressure of the gas such that the particles are now closer to each other, but still there in the gas phase, then yes, their properties will depend on the intermolecular forces between the molecules. Okay. Although in the previous slide, we simply represented the force, the potential, as a function of distance only. In reality, okay, the potential does not simply depend on the distance, but also on their respective angle. Okay, their angles with respect to each other, and also orientation with respect to each other. Okay, so there's an example here, okay, which you can, if you want, you read. Okay, so it's published in Physics Today in September 2019. But then these scientists did a study, and they actually think that, well, they kind of also demonstrated that the models that are used, okay, that are used to represent soft matter can actually be used to represent dense crowds, such as you would find in a bar or in a concert, which is attended by hundreds and thousands of people. Okay, so it's an interesting study, which, if you would like, can take a look. Okay, right. So the first and perhaps the most important, or perhaps most understood type of force that we are going to look into is the electrostatic forces. And these are due to the interaction of two charges, okay, 2-point charges, and magnitude of, suppose you have two particles, right? Particle I and particle J in a vacuum separated by R. Okay, the force acting between them is this C, which is a constant, and that is 1/4 times pi epsilon 0, which is the permittivity of the vacuum. And then multiplication of these charges on these particles divided by R squared. Okay, and the corresponding potential energy is this, again, the C constant. This is again the charges on the particles divided by R plus a constant. This is the integration constant. Now, by convention, we said that we set the potential such that it approaches or it goes to 0 at infinite separation. Okay, the electrostatic forces are inversely proportional to the square of distance, and the potential decays by 1/R. So this is the reason why the electrostatic forces are considered as very, very long range forces, because they decay very slowly compared to other forces that we're going to look into in a few minutes. Okay, these interactions are very strong. However, they might be quickly, how to say, affected by the medium. Okay, so in vacuum, for instance, as the permittivity of the vacuum is obviously very low, right? So if you think about, for instance, the salt crystal, right, which is sodium plus and then chlorine minus, right? The interaction between the charges. So sodium is positively charged and chlorine is negatively charged. So you expect a very strong interaction between the sodium ion and then chlorine ion, right? However, imagine, for instance, take off the salt crystal. The melting point of salt crystal is going to be, I think, above 600. I can't remember exactly right now, but you can Google. Okay, but then you put this into water. What happens? It dissolves very quickly, right? So normally, salt crystal has a very high melting point. Yet, you put it into water. You don't have to even heat the water. Just put it in the water, and then it dissolves, right? Why? The reason is actually has to do with this one, the permittivity constant. Now, because when you put the salt into in water, then you also have to account for the permittivity of the water, which should appear here. Now, the permittivity of water is 79 or 79, I think, 79 point something, or almost 80 times larger than the permittivity of the vacuum. Now, this is in the denominator. So the electrostatic forces acting between the sodium and chlorine ions now are going to be 80 times less than compared to that of in the vacuum, right? And then it weakens, okay? And then the interaction between the sodium and chlorine weakens, and then they dissolve. Also, you have the contribution from the oxygen atoms of water, which are negatively charged. So they would like to, kind of interact with sodium and shield the interaction between sodium and chlorine. And then vice versa, you have the hydrogens, which have plus charges, which would like to interact with the negatively charged chlorines. Okay, so these are the electrostatic forces. And what about the range of interactions? I just told you guys that, the range of the interactions for the electrostatic forces are very long. So I'm pretty sure many of you are doing or are going to do molecular modeling, molecular dynamics, or Monte Carlo simulations based on.
Excuse me?
Yes.
Can I ask you something about the relativity, permeability, related when you're doing like a molecular simulation, if you have like long range forces, how is the relative permittivity included into the simulation? Because I don't recall that is a parameter in there. So how it is computed in a molecular simulation? And that's my question.
Right. It depends on how you treat it. If you're going to explicitly represent the water molecules, then you don't have to change this.
Okay.
But look for implicit water models, okay, which treats the water like a mean field potential.
A continuum medium. Okay.
Yes, yes. In that case, you have to account for this. So you don't treat the water molecules like a 3-atom molecule, but then just like a field of potential. Okay, potential field.
Okay.
Then,
okay.
you have to change for this. Okay. It's called, I mean, people who does, I don't do this. I have, in my entire life, I have never used an implicit water potential because the systems that I looked into never required treatment. They were never large to require a treatment of water as to use an implicit water model. But for instance, those people who do biological simulations, like huge proteins, for instance, right?
Yeah.
If they try to simulate the water molecules one by one, then the cost is huge.
Yeah.
Most people tend to use implicit water models. Am I the person whom to consult about implicit water models? No, I don't know much about that. But I know that, you know, in that case, you have to account for the permittivity. Okay, you have to modify this, right?
Okay, thank you.
Right. So about the range of interactions, so I was just saying that, you know, those who will do or who are doing molecular simulations know that the electrostatic interactions, Coulombic interactions, right? They're treated as long range interactions, right? And right, why the range of interactions matter? Because suppose this is this is the particle of interest, and then if the range is like this, then look, you're looking into, you know, just 3 particles or barely 4, or just a small number of particles that interacts with this particle. But then, as soon as you increase the range, again, this is something that we call cutoff in molecular simulations, then the number of particles increases. Okay, so this means that, you know, this also brings additional computational cost, but usually improves the accuracy. Okay, right. Not only the range is related to the computational cost, but there is this paper from a group I cannot remember, right now, but this is a paper that was published almost like 8-9 years ago. They looked into the interaction of carbon, the weathering of carbon layers. I think the whole thing started with people trying to coat substrate with single layers of carbon, which is graphene, so that to modify their wettability. Obviously, carbon doesn't doesn't like water, and then so this group, I think they did this group did MD simulations, and then they looked into the contact angle of a water droplet on a graphene layer. So what they found was as they increase, so this is graphene, and then as soon as you increase it to 2 layers, then it becomes graphite, which is nothing but multiple layers of graphene, right? So as soon as they increase the number of layers of graphene to 2, right, then they start observing a sharp decrease, right, in the contact layer they have quantified for in their MD simulation. So initially, when the layer was just 1, right, the contact angle of water was 91, but then they put a second layer, the contact angle decreased, and then the third layer, contact angle again decreased, continued to decrease, but not as much as it happened in the first case, right, when they added the second one. So then actually this kind of tells you that, you know, the second layer, first of all, there are 2 things to take away here. One, when you add another layer of carbon atoms, right, they will also interact with the water molecules, and then they will kind of decrease the because of the interactions with the second layer and the water molecules, the droplet will spread slightly more, which will result in a lesser contact angle. Now the third layer, yes, it also has an effect, but because of the distance, the effect is less pronounced, correct? Because the contact angle only now went from 80 degrees to 78 degrees. So, and here, because carbon actually carbon atoms do not have charges here. Actually, although we haven't talked about it yet, but the interaction between the carbon atoms and the water molecules here. The water molecules, they have partial charges. The atoms of the water molecules, they have partial charges on them. They interact through electrostatic forces, but not the carbon and water molecules, because carbon atoms do not have charges on them. So there are no electrostatic interactions, but rather weak dispersion interactions, and they are rather short ranged. So the third layer, as you can see, as soon as they added the third layer, yes, the contact angle decreases, but because these are short range interactions, the effect is not as high as that was observed when the second layer was added. Okay, I mean, if for instance, instead of carbon, if they put a layer of something polar, the effect of the interaction due to electrostatic forces would have been much more significant compared to the carbon water interactions. Okay, right. So now the dipole interactions. Okay, so we talked, for instance, we talked about sodium chloride. These have net charges, or ions. They have these have net charges. However, many molecules do not have this net charge. Right. Overall, the charge is 0. Okay. However, due to when you look into the electron cloud in these molecules, they're distorted. They're not symmetric, right? For instance, ammonia, right? So nitrogen, and you have 1 nitrogen and 3 hydrogens, right? So the nitrogen, it basically draws electrons. Okay, so you have a surplus of electrons near the nitrogen atom. So this is why the nitrogen atom in ammonia is partially negatively charged. And then you have the partially positively charged hydrogens. Okay, so this local clustering of electrons, let's say, okay, this results in what we call a permanent dipole moment, which we represent by this mu, and that is equal to the charge times the distance. Okay, that's the formula that we use to express the permanent dipole moment. The unit is debye. Okay, so right. When I was a PhD student long years ago, I wrote a code to calculate the dipole moment, okay, in a molecule. God knows where the program is, but I kind of feel like I need to revisit that code that I wrote. It's been a long time since I did a calculation about calculating a dipole moment in a molecule, but I did it long years ago as a PhD student. Right. So one thing that I forgot to tell at the very beginning, most of the stuff that I'm going to show, like when I say table, 4, okay, for 1, it actually refers to a table in the book by Prosnitz. Okay, Prosnitz. So I'm going to quickly go back to the yes, and chapter 4 Prosnitz. If you just type in Google Prosnitz fluid phase equilibria, you will find the book. Okay, so all these tables are from chapter 4 of Prosnitz book, who is a very famous physical chemist, I think retired a number of years ago from UC Berkeley. Right. So yes, talking about the dipole moments of molecules. So these are some examples from various molecules. Okay, so carbon monoxide, hydrogen bromide. So some of them don't have. I like there's a space here for a reason. Okay, because as we're going to see, it makes a difference when the difference. So as you'll see practically, when a molecule has a permanent dipole moment larger than 1, okay, whether it has a permanent dipole moment greater than 1 or less than 1 makes actually a big difference, as we're going to see later. And you can see some like potassium bromide that it has a very strong permanent dipole moment. Okay, whereas you have this like HF water and ammonia and this molecule, okay, slightly more than 1. But again, as I said, as we will see, whether a molecule has a permanent dipole moment less than 1 or greater than 1 is important. Right. So right. Think about a molecule. As we said, the potential energy between 2 molecules which have permanent dipole moments does not only depend on distance, okay, but also orientation and their respective their angles with respect to each other. Okay, so and this is the potential energy that gives us the dipole-dipole interactions between 2 molecules. So you have this localization of charges. So one side of the molecule has a partially one side of the molecule is partially positively charged, the other part is negatively charged. So and then, you know, with respect to a certain axis, the axis, they have these angles and the orientations. Okay, right, and then you have this formula that expresses the potential energy between two permanent dipoles. Okay, so right, but okay, obviously these they don't simply just sit there in a single orientation, right? I mean, perhaps there are infinite number of configurations that they may take, right? These molecules with permanent dipole moments. So it's going to, so as we're going to see in the next slide, okay, we kind of we tend to take an average of these orientations. Okay, before coming to that, one thing that we have to mention is that, so obviously, speaking of these orientations, obviously the most energetically unfavorable, thus unlikely configuration is when you have the like charges close to each other. So that's very, very unlikely. Okay, but then you have the most energetically favorable configuration, and that is most likely configuration, where the charges, but the alike charges are close to each other, aligned such that, you know, they're close to each other. Okay. So electrostatic interactions tend to orient the molecules. The thermal energy, kinetic energy, tends to disorient them. So what we're trying to say here is that if it was just left to the electrostatic interactions, right, they would, because they're quite strong, these dipole-dipole interactions and also electrostatic interactions, the molecules would align themselves purely with respect to the electrostatic or dipole-dipole forces, right? But the thermal energy works against this. As the temperature increases, the thermal energy rotates, okay, or disorient the molecules. So then at higher temperature, okay, actual thermal energy becomes more dominant, all right? And the order that is observed in polar gases at low temperatures, which are purely again based on the electrostatic or dipole-dipole interactions, tend to disappear as temperature increases. So there is like an inverse relationship between these electrostatic or dipole and dipole interactions with increasing temperature. Okay, and at increasing temperature, these polar gases start acting like just any other normal gases. Okay, right. So now going back to what I said, many orientations, right? So they don't simply just sit there in a single orientation, but then they actually can take different orientations. Now, the probability of these orientations is proportional to the Boltzmann weight of this particular orientation. Okay, so as I said, you know, this would be a less likely configuration, whether this one is going to be a more likely configuration or orientation, right? But then we kind of take an average, and we take the average of these possible, say, orientations, and then weigh them according to the Boltzmann factor. Then this, okay, this then becomes this, okay? And also temperature, as I said, is important in the case of dipole-dipole interactions. Temperature is important. As I said, the thermal energy disorients the molecule, so it has to be taken into account. This is actually an expansion, but then we are just simply taking the first term. And to be honest, I'm not aware of the second or third terms. I don't know, but there are these higher terms, but I don't remember seeing them. But then, okay, this is the first term of the expansion, which is usually sufficient. But one thing that we have to take note is that you can see that the dipole-dipole potential now decays. So R now is in the denominator, right? Decays with 1 over R to the 6th, the 6th power of the inverse distance. Okay, as you can see, the dipole-dipole interaction decays much faster compared to the electrostatic interactions, this point charge interactions. Okay, right. Then there's one other thing that we have to also remind ourselves, this is why I told you that it makes a difference when the molecule has a dipole moment less than 1 or greater than 1, because you can see that, okay? Here, the potential is a function of the square of the dipole moment of the molecule I and molecule J. So for instance, carbon monoxide, which has a small dipole moment, 0.1, you square it. So if you're just talking about a pure carbon monoxide gas, so this is going to be same basically. So we're going to talk about 0.1 squared, which is going to be 10 to the minus 2, multiply with another 10 to the minus 2. So it's going to be in the order of minus 4. Okay. But imagine, suppose we have HF here, which has a dipole moment almost 2, right? 2 times 2 to the squared 2 is 4. 4 times 4, 16. Okay, so you can see the difference. The square makes things, because the dipole moment is squared here. That's why having a dipole moment less than 1 and greater than 1 is important, is significant. Okay. Yes, we talked about this. Right. Good. Next, we can just quickly discuss these questions. I mean, like some of you can just turn on the mic and try to answer. Is the heat capacity at low pressure a configurational property? It's not, right? Because when it's only in dense. What we mean by configurational property is that, you know, a property that depends on intermolecular forces, but at a low pressure, a gas molecules are far away from each other. So intermolecular forces are not significant or perhaps negligible. So no, this is not a configurational property. How does the contact angle for water on graphite change with the number of graphene layers considered as part of graphite? It decreases, and then this has to do with the range of interactions, right? First, with the addition of the second layer, remember the decrease in the contact angle was greater compared to the decrease in the contact angle when the third layer was added, because the range of those interactions was short. Okay, so the reach of the third layer was not as great as the reach of the second layer. Okay, which we explained in this one. How does the dipole-dipole interaction scale with temperature? Okay, so it's inversely proportional, right? Remember? Yes, it's inversely proportional. Okay, right, now induced dipoles. Okay, we still have some time until we give a break. Again, many molecules actually do not have permanent dipoles, like methane, for instance, it doesn't have a permanent dipole, okay? However, when they expose these molecules to an electric field, depending on obviously the strength of the electric field and its direction, right? Then you can actually move the electron clouds, okay? So, for instance, methane is a perfect tetrahedra, right? Okay, but then under the it's under the electric field, you can distort this perfect symmetry or tetrahedra of methane, and then you create an asymmetry, right? And then you have obviously in the nucleus, you have the proton, which is positively charged, you have the electron clouds. So now, rather than being symmetric now, and under the effect of an electric field, you have some sort of polarization, right? Okay. And this, again, this is proton or nucleus, right? And then you have the electron cloud. So because of this, now you have this, what we call this induced dipole, okay? The way we express the induced dipole when they are subjected, when a molecule is exposed to electric field is, in this dipole, we have this prime so that, you know, we differentiate it from the permanent dipole, okay? It's polarizability times the electric field. The polarizability is a molecular specific property. And if we look into the next slide, again, this is from Prouslet's book, right? You can see that you have a range of polarizabilities. You know, for hydrogen is small, but then as the molecule gets larger, the polarizability also gets larger. The reason is because in small molecules, the distance between the electron cloud and the proton nucleus is very short. So it takes a larger, say, electric field to kind of distort that electron cloud away from the proton. Okay, whereas in large molecules, the distance between the electrons and the proton is larger, so that's why they are polarizable. That means that they are susceptible to the presence of an electric field. Okay.
Is the polaricity denoted on temperature, or?
That's that's a good question. I do not know, but probably it's not. But if someone knows the answer to that, they can answer.
I don't know. I mean, I was asking because it says average. So if it's an average, what are you averaging for respect to?
I don't know the answer. Sorry.
Okay.
Is polarizability? I mean, look, among all I have done the calculations that involves polarizability. In those simulations, did I care about the temperature? No. Okay, but that doesn't mean that that doesn't mean that the polarizability is not a function of is not dependent on temperature. Perhaps it depends, but then the dependence could be kind of
weak.
Yeah, and then you don't really care about it. Because actually taking the polarizability into account in a molecular simulation, it's computationally very expensive. I'm going to mention something in a few minutes or perhaps, but because there's polarizability and then there's back polarizability, and solving that and then you have to solve this as a consistent. Anyway, so the calculation is very demanding computationally. Okay. So in many cases, I mean, polarizability already makes things complicated, and then as I said, I have never thought about the effect of temperature on the polarizability, which would probably make things even much more complicated.
Yeah.
But yeah, I probably after this I'm going to Google whether to do about it. So thanks.
I will too.
Okay, very good. Thanks. Right. So yes, in this dipole interaction, this is the expression here. So this is the polarizability of the molecule I, and then this is the permanent dipole, square permanent dipole of the particle J. Okay, because this dipole literally polarizes the particle I, and vice versa. Okay, the permanent dipole on particle I polarizes the particle J. This also so there are two important things here. One, this potential is always attractive, and two, if there are no dipole moments, then that means that there is no induced dipole moment to talk about. So for an induced dipole moment, you either need to have an external electric field. Okay, if you don't have an external field, for instance, a point charge can create an external field, or you can artificially generate the external field. But induced dipole can be induced by a molecule that has a permanent dipole. Okay, right. So and what I was telling you about back polarization is that, for instance, a molecule that has a permanent dipole polarizes the other one, other molecule, which now has an induced dipole, which is added on top of the permanent dipole. But then, because of the increase of this dipole moment on, say, molecule B, now it back polarizes, the molecule A. So this goes until this goes back and forth until you reach the you converge to a certain level. Okay, because I know that from our molecular mechanics simulations, suppose adding polarizability increases the computational cost by, say, 3 or 4 times, and then if you include back polarizability and solve the equations as a self-consistent field, then I think the computational cost increases by about an order of magnitude. This is my personal experience. In most often cases, in molecular mechanics simulations, we ignore back polarizability, and usually just including the first polarization, is fine, is good enough, right? Yes, and one thing also to not to forget, as you can see, there's no temperature term here. Okay, so when it comes to temperature, so when it comes to induced dipole interactions, temperature does not have an effect. This is different than, remember, the dipole interactions, where the temperature disorients or rotates the molecules, and then this becomes particularly important at high temperatures. Whereas in these dipoles, they are independent of the temperature. Okay, good. Dispersion forces. I'm going to talk about this and then take a break. Okay, I think that's the format. I don't intend to keep going for 2 hours. Okay, right. So yeah, London forces, so dispersion forces. These were first actually formulated by London, but actually this has nothing to do with the City of London. Actually, this has nothing to do with England or UK. This was a German scientist, Fritz London, who actually spent most of his time in Germany and later in the US. I think he spent some time in Oxford, but mostly, he was away from United Kingdom. But then his last name happened to be London. Okay, so Fritz London. Anyway, so now, so he observed that on average, molecules, when they're observed over a long period of time, they're non-polar. But the fact is, the electrons keep oscillating around their ground state position. Okay, and because of this kind of oscillations, all right, they generate these temporary dipole moments. Okay, and then these temporary dipole moments, they will kind of stimulate induced dipole moments on other molecules. Okay, and then the temporarily created induced dipole moments, then they will back induce other dipole moments, and then this whole thing basically like a chain reaction. Okay, it continues. So these resultant forces is the induced dipole interaction. But because London brought this up, I mean, he was the first one to formulate this or to present this. We now kind of call them London forces or London interactions. Okay, these are right, and this is the formula for the this is the formula for these London dispersion forces. They are dependent on 2 molecular properties: polarizability. So suppose you have particles I and J, separated by R, right? Before, sorry, one thing that I forgot to say: the induced dipole moment is also it also decays with scales with 1/r⁶. And okay, London dispersion forces, same. They decay with inverse r⁶, but they are a function of molecular properties. First, polarizability. Second, first ionization potential. Okay. Now, if you're talking about the same molecule, then this equation simplifies to this one. Okay. And as it is the case in the previous formula that I showed, this is independent of temperature and decays with the 6th power of the distance r, 1/r⁶. Okay. Let's look at the so we talk about the polarizability. I think I showed the table about polarizabilities. Yes, so we have this table, okay, that shows the polarizabilities, and we mentioned that for large molecules, the large molecules are more polarizable, right? And then you have this ionization potential for different molecules. The ionization potential for smaller molecules tend to be higher, again, because the ionization potential is the energy required to basically take away one electron. So in smaller molecules, and because of the distance between electron and the nucleus, it's difficult. Okay, the energy is required is higher, whereas it tends to be lower in larger, generally, again, larger molecules. One thing that we need to keep in our minds is that this potential, okay, is for most known, I mean, for most of the molecules that we deal with, this is the London dispersion forces are about the same. And this is because the polarizability and ionization potential is kind of inversely related. For instance, the larger the polarizability, the lower the ionization potential. Because polarizability actually, remember, ionization potential is the amount of energy that is required to take away one electron. Okay, so if it's easy to take an electron, that means that it also means that it's polarizable. So it's susceptible more to the electric field or forces around themselves. Okay, so this is kind of inversely related, and because of this, this whole thing is about the same. Not obviously exactly the same, but it is in the same order of magnitude. Let's put it this way, for most molecules that we know or that we deal with. And this is due to the inverse relationship between the polarizability and ionization potential. Right. And these are some ionization potentials, again, from Prost's books. Okay, so we talk, okay, aside from the electrostatic potential, which is the most important and the strongest and the most far-reaching one in terms of range, which one, the question is, which one is more significant, right, in terms of molecular intermolecular interactions? Dipole moment, induced dipole moment, or dispersion? But so let's try to answer this, and then we'll take a break. Okay. In all these equations, except dipole, they are independent of temperature. So we have the temperature here. Suppose we assign temperature, say room temperature, okay, 300 Kelvin. And then, because they all decay with inverse 1 over r to the 6, okay, you can see, we can also cancel, we can basically ignore r to the 6, okay? And then we can compare them, right? So this next table, again, which is from Prost's book, at this temperature, and this is the Boltzmann constant, right? So we suppose we call the parameters other than r to the 6 as b, okay, b, right? Yes, so we denote this minus b over r to the 6. B basically stands the remainder of the equation after ignoring r to the 6, right? And they're all negative, attractive. So for these molecules, we're going to compare the dipole interactions, induced dipole interactions, and dispersion interactions, and then let's see which one is more important or significant. Now, when there is no permanent dipole moment, you can forget about the dipole interactions or induced dipole interactions. This is, think about methane, for instance. You put methane in a box, there's no electric field. The only type of interaction that the system will have is the dispersion interaction. Okay, so it's always going to be there. You can see. For something like for carbon monoxide, which has a very small dipole moment, the dipole and induced dipole interactions are going to be negligible. Whereas you see there's still significant dispersion interactions. Now, as the permanent dipole of the molecule increases, so does the dipole interactions and induced dipole interactions. But one thing you can see is that the dispersion interactions are always there. So actually, overall, the dispersion interactions are perhaps the most important interaction. Okay, so something that we can never neglect. It's always there. They're always there. The dispersion interactions are always there. Whether, on the other hand, the dipole and induced dipole interactions, they depend strictly on the presence of a permanent dipole. Okay. So usually the contribution of the induction forces is usually very, very small. Even for a strongly polar substances, this dispersion forces generate a large contribution, so they can never be neglected. Right. What I'm going to do is I'm going to leave this on the screen for a couple of minutes. Okay. You can just do some brainstorming. I'm going to take a 5-minute break, take a glass of water, and then we will continue after 5 minutes. Hope that's okay. All right. So I'm going to just mute myself and then turn off my video, but I will be back in 5 minutes. Okay, and then we'll continue. All right, hi again. And right, we can just quickly answer these questions and resume our class. How do electrostatic forces between two atoms change when the distance between the two atoms is doubled? Well, remember the forces decays by what, 1/r², right? So if the distance is doubled, then the force field decreased by 4, right? How do dispersion forces between two atoms change when the distance between the atom is doubled? So that's r⁶, correct? So they decay much faster. What types of interactions can you never ignore in assessing the properties of fluids? That's dispersion interactions, as we have shown in the previous table. Okay, so far, well, then we'll go to the next slide now. Yeah, so far we talked about attractive forces, right? What about repulsion? This is about actually it's quite straightforward, but then when two molecules come close to each other, the electron clouds repel them, okay? And then when the distance is very short, actually the repulsive forces can become very high, okay? The repulsive forces can usually be represented by with a power law, okay? Shown in this, like similar to shown here. So this is a positive constant divided by r⁴. N is usually between 8 and 16. Okay. So this is always positive. Positive, remember, means repulsive. Okay. Negative, attractive. Right. So actually, this is it about the repulsion. But suppose we combine the repulsive interactions and in attractive interactions into one equation. And then we represent the repulsive part as A divided by r⁴ minus B divided by r⁴. Again, minus B, remember, in this table, we are referring by minus B to these, dipole, induced dipole, and dispersion interactions. And they're all positive constant. A, B, and M are positive constants. Now, this is called a Mie potential, okay? So it's represented like this, but then we can convert this into kind of a more meaningful equation by defining two terms, which is the first one is the sigma, and sigma is the separation at which the potential is 0, okay, and epsilon is the minimum of the potential, okay, the minimum value of the potential. Then this thing can be written in the following form, which is kind of more complex, okay, but then more meaningful. Now we write something in terms of the characteristics of a potential. One is sigma, where the potential is 0, the separation at which the potential is 0, and then epsilon is where the minimum point of the potential. Okay, and then if we set n to 12 and m to 6, okay, as demonstrated by in the case of London dispersion forces, we end up with this potential, which is commonly known as the Leonard-Jones potential. Okay. Indeed, if R is set to sigma divided by sigma is 1. 1 to the 12 is 1. So this part is 1. Minus, again, this part is 1. 1 minus 1 is 0. Okay. So the potential is 0. Okay. So characteristics of the Mie potential is, so this is the Mie potential. So we're going to set the attractive part, the power for the attractive part, which is m, to 6. Okay, and we're going to play with the n. So we'll set it to 9, 12, and 18. So what you can see is if n is larger, then the initial part of this potential is steeper. Okay, and also it has, and then if it's set at a lower value, such as 9, then it's less steep. This has an effect on the location of the minimum of the potential energy. It also has an effect on the range of the potential energy. If n is 18, which is more repulsive, then the range is shorter. Okay, but then if n is 9, the range is as you can see, it's slightly longer. Okay. Right. And actually, I'm going to give an example. Hopefully, we will have time, but I'm going to give an example from our research. We can fit these sigma and epsilon to physical properties, such as vapor-liquid coexistence curve, or phase equilibrium properties. And we'll talk about this later, hopefully. Right. So far, we talked about these models. Again, these models are approximations, but I think, we come to the point that these models are quite accurate. But if you want really, very, very high accuracy, obviously, the ab initio calculations are the standard. In this paper, which was published in about 8 years ago now in Science, for instance, they show that they can reproduce the lattice energy, and also they can predict the conformation of a benzene lattice by very high level ab initio calculations. Okay, so there's also a possibility that you can reference your approximate models with respect to ab initio calculations. You can check their accuracy, not just experimental data, but if you run high accuracy quantum calculations, then they can also be used as verification means. Okay, right. Finally, I think that's done from the final hydrogen bonding and some other interactions. Yes, hydrogen bonding is actually interesting and very important. Okay, it has an effect on many things. First and foremost, perhaps water. Every time we talk about we think about hydrogen bonds, you think about water. Okay, but it actually happens. It can happen in any. It doesn't have to be like an HO. Okay, it can happen in HF or other things, as long as you have a sufficiently negative atom that is next to the hydrogen. You can. There is the possibility of having a hydrogen bond. Okay. For instance, in some gases, is such important. These hydrogen bonds are such important that actually it results in the vapor phase. It results in clustering. For instance, in HF, you have these kind of chains of HF, and then depending on the pressure and temperature, you may find up to 6 HF molecules that are that aggregates due to these hydrogen bonding. Okay, right. Fine. An importance of hydrogen bonding in nature, I mean, the whole our DNA depends on the correct positioning of the DNA depends on the hydrogen bonds. I mean, protein folding, self-assembly of biological molecules. The hydrogen bonding is extremely important. The hydrogen bonding is much stronger than the dispersion forces, but again, significantly lower than covalent bonds. Although, for instance, in HF, the hydrogen bonding is up to 155 kilojoule per mole. But other than in individual molecules, they range between 8 to 40. Okay, you can see some actually in water, it's not that strong compared to, for instance, where the hydrogen bonding is with a nitrogen molecule, nitrogen atom. Okay, so these are taken from this reference. Okay, and then covalent bonds, they are in the range of 200 to 400 kilojoule per mole. The hydrogen bond effect usually decreases as temperature increase because of the thermal, again, fluctuations, which tend to rotate or distort the molecules. Because the orientation is also important in the formation of hydrogen bonds. Okay, so rotation of the molecules affect, and temperature, facilitate distortion of or rotation of molecules. So they're susceptible to hydrogen bonds, are susceptible to increase in temperature. Let's illustrate the effect of hydrogen bonding. You have ethanol and dimethyl ether, which have the same formula, but structurally they're very different. In the case of ethanol, you have OH literally sticking at the end of the molecule, but then here oxygen is kind of protected. Okay, and as a result, the boiling point of ethanol is 78, whereas dimethyl ether is minus 25 degrees Celsius. That means that this is at room temperature liquid ethanol. Dimethyl ether, on the other hand, is a gas. And again, because of the attractive forces due to hydrogen bonding, the enthalpy of vaporization of ethanol is more than twice the enthalpy of vaporization of dimethyl ether. Solubility, I mean, you have ethanol, it's infinitely soluble in water, whereas dimethyl ether is slightly soluble. Okay, so here's an immediate effect of hydrogen bonding in isomeric molecules. Okay, I mean, their formulas are same, right? Finally, the solvation forces. This is actually, this has to do with kind of what we discussed at the very beginning with Gustav's question, right? So normally you have two molecules interacting with various forces. If there is vacuum, there's nothing. That means that, you know, that for those forces are not shielded. But then if you have these small molecules as solvent, okay, and then depending on the way they pack or they organize themselves between two particles, they may have a very important, they may have a significant effect, or sometimes not very significant effect in the interaction between two particles. Okay, so the potential will be mediated, right, by the presence of the solvent molecules, and so this is the potential of mean force. Okay, expressed as the multiple of sigma. That's the thickness of one molecule. Okay, so when there is, the potential is negative when there is no layer of solvent or like disorganized solvent. Okay, then these are the parts that you get negative potential. But then if you have layers of these solvents, you know, properly organized, then the potential will be positive, and it's going to be positive, more positive in the case of one layer compared to two layers. Okay, this corresponds to two layer, and then this corresponds to a single layer, because it's always more difficult to remove this last remaining layer of solvent molecules. Okay, that's why this is kind of relatively more positive. This peak here, it's more positive compared to the other peak. Okay, good. And for instance, an example from practical example, carbon nanotubes. You know, several groups are working on carbon nanotubes, but then to use them in any application, you need to make them soluble in water. I mean, you have carbon, right? Pure carbon. It doesn't like water, right? They aggregate, make clusters. So kind of to disperse them, they coat these with carbon nanotubes with surfactants. And because of the surfactants, in case the carbon nanotubes come close to each other, they will repel them. Okay, so this is kind of an example of this solvation forces. Right. This is an important. This is actually a bit not related to the solvent forces, but just an example from common literature, recent literature about the importance of molecular interactions. It talks about, so if you go to this paper, it talks about this transport channels, proteins that facilitates the transport of important molecules through cell membranes. And it talks about a case where an entire family living in some part of the world cannot feel the pain, because it turns out that one of the channels that are responsible for the transport of sodium ions malfunctions because of some certain genetic disease in the family, and because of this, the whole family cannot feel anything like pain. Okay, so sodium is an important molecule that is that facilitates the the communication between our senses and then our brain. Okay, so if there is a malfunction, at the molecular level interaction, then that the whole thing breaks down, right? So this is why interactions at molecular level is important to know. Okay. Right. So let me see how many minutes do I have. Yes, I think we're going to finish in 10 minutes, and I'm going to show an example from our recent research. So what do we know about repulsive forces? Well, they repel each other at they're important at short ranges. When is the hydrogen bond important? When is the hydrogen bond important? At low temperatures, right? At high temperatures, the hydrogen bond, first of all, becomes less important because of the thermal fluctuations, but also in biological systems, right? In living in live cell, living cells. Yeah. Do you think it's essential to have an O and H atoms for hydrogen bonds to occur? The answer is no. Okay, the answer is no. Next to it, you have a nitrogen atom. Okay, and then you can have the important thing is that you need to have a sufficiently negative atom next to hydrogen. That's the key, right? When do solvation forces arise? When you have solvent molecules packing around molecules, okay, thus mediating the interaction between these molecules, which is a solute. What is the range of interaction between two colloidal particles dispersed in a solvent due to solvation forces? I think this has to do with the graph that kind of, yeah. So I would say probably by looking at this, because this is a function of sigma, you know, several layers of the range is basically several layers of the solvent molecules, right? That's the range. 3, 4, 5, perhaps. Right. So now the rest in 5, 6 points, I'm going to kind of go into history of science. So going back to the hydrogen bond, the IUPAC description of the hydrogen bond is the following: an attractive interaction between a hydrogen atom from a molecular fragment D H, in which D is more electronegative than H, and an atom or a group of atoms in the same or a different molecule in which there is evidence of bond formation. So this definition, IUPAC definition, is taken from this reference. Now, the hydrogen bond was first presented by Sutor in these publications that appeared in Nature and Journal of Chemical Society in 1962 and 1963. So they're almost 60 years, right? 60 years by Sutor. And then Sutor was the first one to talk about the hydrogen bond, the existence of these bonds. And then Sutor was referring to this carbon, H, and oxygen, right? Okay, right, this was the first time, almost 60 years ago. So what they said was hydrogen bonding involves a shortening of the van der Waals distance between the atoms concerned. So the bonding was not simply explainable by looking into, you know, the van der Waals distances. Okay, what is observed in the case of hydrogen bond was, you know, shortened, right? The distances were shorter than the expected based on the van der Waals diameters. The donor and then the acceptor of the atoms are usually the most electronegative of the elements. Yes, you have the donor and then the acceptor. The electronegative elements such as, you know, fluorine, oxygen, nitrogen, and fluorine, but a CH group that is activated by groups promoting ionization or partial ionization can also take part in hydrogen formation. And the distances that are reported in these articles were referring to nanometer, well, fraction of a nanometer, right? 2.26 angstrom, 3.40. And actually, these are, you know, nowadays, this is such an accurate, although it was like 60 years ago, this is such an accurate description of the hydrogen bond. Even today, we rely on almost, you know, some of you would have already calculated, or perhaps will calculate, radial distribution functions to detect hydrogen bondings, and then these are the two characteristic distances that we look for when we try to detect hydrogen bonding. There is also orientation involved, but these are two characteristic distances, okay, of hydrogen bonding. And these were measured almost 60 years ago. But what happened was, after Sutor published this very influential crystallographer who lived in California wrote a book chapter in 1968, and he said in this book chapter, the CH, you know, oh, hydrogen bond, what is it? And then he concluded in the chapter, the answer to the question in the title of this section is, it isn't. So basically, he refused to recognize the existence of the hydrogen bonding. The thing is, you know, this person was a very influential person, and then for many years, people, although they observed the same findings of Sutor, they were afraid of openly, you know, expressing their findings. They called it something else. They didn't call them hydrogen bonding. And this person, Jerry Donohue, was a prominent scientist who had shared an office with Watson and Crick, the inventors of DNA. Okay, he wrote crystallographic books, right, read by almost all crystallographers in the world. So what he said was very influential. And this person, Carl Schwab, said this type of hydrogen bonding became almost unmentionable. Okay, so people were afraid to talk. For instance, this person in his PhD thesis did not consider these hydrogen bonds, even though I was practically looking at them. Scientists in the US were scared to use the words the hydrogen bond, one reviewer wrote, I wouldn't call them hydrogen bonds, I would call them suitors. But then, obviously the truth will sooner or later will come out, and to vindicate suitor in the 70s, Taylor and Kennard collected many data in agreement with the original proposition. So it's been it had been almost 10 years since suitor published the findings, but then, it took almost 10 years to kind of break the stigma in the scientific world, and then, more people supported the findings of suitor. So any powerful scientist should be very careful when criticizing an idea, because it can have a strong negative effect on the field. And I didn't give you the first name. Suitor was a female scientist. June Suitor was born in 1922 in New Zealand, came to Cambridge to get a second PhD after doing a PhD in New Zealand, and taught at Birkbeck College in London, which is now situated right across UCL, where she became an interested in electronic computing. After a short break, she joined Kathleen Lonsdale at UCL in 1966 to study bladder stones. By the time Dono published his book chapter, she was studying Napoleon III's bladder stones. In 1981, she had become interested in theoretical aspects of stone growth. So actually, because of a decrease in her sight, she started working. She switched from experimental work to computational work. But the thing is, by 70s, she was already working on crystal growth, and then she was actually working on the specimens taken from Napoleon Bonaparte's bladder. I think Napoleon III is Napoleon Bonaparte, but I'm not really sure. But bladder stone, I think it's Napoleon Bonaparte. But the thing is, by the time the world was involved in discussing whether the hydrogen bond exists or not, she actually stepped away from that field and then started working on crystal growth, stone growth. But the thing is, for 6 or 7 years, because of some effective inflation crystallographer, she wasn't recognized. She didn't get the recognition she deserved until many years later. Okay. So that's it. That's the end of the fundamental that I would like to present to you. Before I switch to some other, my next presentation, do you have any questions at this point from the audience? We don't have many people, but in the chat. Well, okay. If you have any questions, let me know. Otherwise, what I want to do is I want to show you, I want to talk about how, actually, let me go back. Again, is there any questions so far? All right. So what I would like to do is, how do we fit force field parameters? Okay, because remember, we talked about this. We mentioned how we represent all these, repulsive and attractive forces. The attractive forces are coming from, dispersion forces, induced dipole or dipole interactions. How, we kind of managed to sum them up, represent them in Lennard-Jones potential, right? And then remember, there was also electrostatic potential. Okay, so that means that gives you the idea that by using electrostatic potential, like a Coulomb potential, and the Lennard-Jones potential, or let's say Millet's potential, okay, we can actually model many systems to a satisfactory degree, right? But then how do we come up with these parameters? How do we fit these epsilon, sigma, and all these charges? How do we do this? My next presentation is about that. And it's actually my own work, which I did over Christmas time. And then I submitted this to JPCC. Okay, it's under review right now. I'm not perhaps supposed to share this because it's under current review, but that's okay. I'm not publishing it yet. So, and I'm going to kind of, without going much detail, I will try to present what I have done, okay, what it takes to kind of fit a force field. I know there was a session last week which discussed using AI, machine learning to fit force field parameters. But this is kind of the old, I don't want to say old school, but this is current as people use it. But this is kind of fitting force field parameters with respect to experimental data, okay? So the title of the paper is, by the way, this is my name, okay? I'm not Alberto Striolo, okay? Alberto Striolo is the one who prepared that presentation that I presented to you, slides that I presented to you. My colleague Alberto left UCL now, and my name is Ozgur Yazaydin, okay? So this is me. Anyway, so the title of the paper is 1-bromopropane capture with hydrophobic zeolites, force field development and molecular simulations. Now, why did I get interested in 1-bromopropane? Because a year ago, United States Environmental Protection Agency, after some surveying and then looking into data, concluded that 1-bromopropane, which is a solvent used in various applications, is quite dangerous to human health, including like probable carcinogenic, having carcinogenic effects. And then they kind of now they're going to bring some controls over the use of 1-bromopropane. So then I thought, okay, why don't we capture, and this is kind of related to my research because I work with porous materials. Why don't we capture through adsorption, using porous materials, 1-bromopropane that is released to atmosphere by using some zeolites. Zeolites are porous materials. Okay, then how do you do a molecular simulation, right? If you're not doing quantum simulations, so you have to have a model that represents the electrostatic forces and those dispersion forces. Okay. So here you go, the non-bonding interactions. So this is the Coulombic potential, where you have potential charges, right? Partial charges that are located on atoms of a molecule, IJ, and then you have the Lennard-Jones potential. So I need to find three things here. One, actually, I need to find four things, or three things. Let's say, well the partial charges, right, on the molecules, and the sigma and epsilon of the molecule. So we did that, but then how I did it? Okay, the first thing to do is finding the partial charges on the atoms of bromopropane. Now, bromopropane, I'm going to go to the S side, is this: CH3, CH2, CH2, and bromine. Okay. So what you do is you do a quantum chemical. So remember what we did in the when we are discussing about induced dipole interactions or dipole interactions. This is a neutral molecule. Okay, it doesn't have any permanent. It doesn't have. It's not an ion. The overall charge is 0. But then each atom, okay, has a partial charge on it. Okay, and then you can do this calculation by running DFT calculations. So what you do is you optimize the molecule, okay, and then you calculate the electrostatic potential, and there are schemes that you fit partial atomic charges that are located on each atom, which reproduces the electrostatic potential around this molecule. So collectively, those charges will reproduce the electrostatic potential that is calculated from the quantum chemical calculation. Okay, right. The next step is a simplification, actually, which is very useful. Usually, we sum these hydrogen atoms into the heavier atom. So we represent CH3 as a united atom. It's a bead. We represent the CH2 again as a bead. Obviously, we sum the charges, and also we sum the mass. Okay. So what you have at the end is what we call a united atom. We don't do it for bromine because it's important to treat the bromine here explicitly. But what you have is a united atom model, which is made from literally which consists of 4 sites: CH3, CH2, CH2. Okay. So, but then we now have calculated charges. So, for instance, this -0.106 is nothing but summation of these 4 charges. Okay. Right. So this is the first step. Why did I do this? Again, to account for the electrostatic interactions, correct? Right. The next step is, now obviously these will be yes, I mean, because as I said, because we do not the bromopropane is a neutral molecule, but that doesn't mean that it doesn't have any permanent dipole moment because of the or induced dipole moment, because of the presence of these partial charges, local charges. Okay, we have to account, and we represent these forces used through a Coulombic term here, and for that we need to compute the charges, which I illustrated, okay, to you. Now the next thing is to determine the sigma and epsilon of the Lennard-Jones potential, and here comes the final check. Okay, so we compute certain vapor equilibrium properties, okay, and from simulations, and we compare them against experimental data. Okay, this is literally a trial and error method. Okay, obviously from literature you can get some good estimates, a starting point, but you literally assign, you do educated guesses, and then you assign epsilon and sigma to each united atom. Okay, and there's also some intramolecular potentials, which represents for the vibrations between these united atoms, and then like angles and torsion. I'm not going to go into that. I think 2 weeks ago there was a presentation about that, about the force fields. But what we do is we do Monte Carlo simulations, okay, in the Gibbs ensemble to basically represent vapor liquid equilibria, such that from these simulations, which I'm not going to go into the details, but I would like to perhaps in the future, because I do lots of Monte Carlo simulations, right? But from these Gibbs ensemble Monte Carlo simulations, actually we can model the vapor liquid equilibrium of fluids. For 1-bromopropane, we do that, okay? We did that. I'm going to, yeah. So this is the, oops, sorry. Yeah, okay. So this is the vapor liquid coexistence curve of 1-bromopropane. The dots are, or the circles, closed circles are computation simulated data. The densities of 1-bromopropane in the vapor phase as a function of temperature, and the liquid phase as a function of temperature. Okay, so this is temperature, and these are densities in the vapor phase, and then in the liquid phase. The squares and triangles and these diamonds, that are experimental data. Okay, so by basically playing with the epsilon and sigma, you try to reproduce this vapor liquid coexistence curve. Okay, and then we do Gibbs ensemble Monte Carlo simulations in which we explicitly reproduce a liquid box and a vapor box, and in which molecules we sample molecule transfer between liquid phase and vapor phase through Monte Carlo sampling. Okay, and out of these Gibbs ensemble Monte Carlo simulations, we obtain these vapor liquid coexistence curve, which is nothing but the densities of the 1-bromopropane in the vapor phase and in the liquid phase. We can also calculate from the Gibbs ensemble Monte Carlo simulations the vapor pressure of 1-bromopropane, and again compare that against the experimental data, okay, as a function of temperature. Again, here the closed circles are simulated data, and the triangles are experimental data. The agreement is quite good, okay? And actually, for instance, the predicted boiling point is the following. This is experimental, except the critical pressure, and this is critical temperature, critical density. The agreement is actually, I would say, excellent, except the critical pressure. And actually, that has to do with the fitting. Hopefully, this will come out, and then you will read it, why it does a poor. This actually doesn't have to do with the model, but it's rather the underestimation of the critical pressure has to do with the fitting method. But again, I'm avoiding the too many details now. Okay, but why did I fit the force field? Why did I fit my force field against vapor liquid data or phase equilibrium data? Because there's a reason for that. Now, it has to do with the fact that this part of the study, capture. Now, how do we capture bromopropane from air? By using zeolites, which are porous materials, which are very narrow pores, like in the order of, say, 5 angstrom to maximum 15 angstrom. So we talk about like 1-2 nanometer scale, okay? Now, what happens is, in confinement, the phase behavior of fluids are very different than they are in the bulk or in ambient temperature, okay? So the fluid molecules or the fluid itself may undergo a phase change at temperatures very different than they are supposed to go under this phase change when they are in ambient state or in bulk phase, okay, in bulk. That means that if you would like to predict the presence or absorption of molecules in confinement, that is in narrow pores, if you can develop a model that reproduces the phase equilibrium properties of the fluid, then there's a very good chance that that model is going to work also for predicting the behavior of that molecule in confinement. Because in confinement, as I said, the presence of molecule is very specific. It's the phase behavior of the molecule is very specific. It's different than it is in the bulk. Okay, it may undergo, for instance, it may become more condensed, okay, or dense at lower pressures, okay, compared to bulk. This is why fitting the force field with respect to vapor liquid equilibrium in this case is important, or is a reliable way of creating a force field. So we did that, and we screened more than 200 zeolite structures, okay, at different concentrations of 1-bromopropane in air, and then we found the most promising zeolites that can be used to capture 1-bromopropane from air, okay? And at the end, I don't know if you guys deal with zeolite, if any of you deal with zeolite, but again, these are porous materials. We know more than 200 of them. I think we 237, and they have like they are given these 3 letter codes, okay? And this MRE and STW zeolite turned out to be the best, okay, zeolite for the concentrations of 1-bromopropane detected where it is used in industry. Okay, so there you go. You know, this is a very nice application of how one can fit force fields to against experimental data. I mean, by using some quantum chemical calculations to determine the partial charges on atoms, but also by literally by trial and error, you fit sigma and epsilon so that you produce the phase equilibrium properties of 1-bromopropane. Okay, yeah, this is it, guys. If you have any questions, please let me know. I'm here. But the thing is, it all ties back to the interactions, forces that we discussed at the first part of my presentation today. Remember, there were the electrostatic forces. There were different types of dipole-related interactions, dipole, induced dipole, and then even weaker, but more important, but very important, is dispersive forces that was first identified by Fritz London, okay, and which we represented in this very simple equation, which actually makes really, as you have seen, it really works. Although simplified greatly, it literally works to kind of reproduce the experimental data. Okay, so this is why I wanted to show this my recent paper that is currently under review. I want to share this with you. Right, I talked too much. We still have some time for questions. If you have questions, feel free to ask. No guarantee that I can answer, but I will do my best.
Yeah. Which force field did you use for the zeolite? Oh, there, yeah.
It's a very good question. Obviously, which force field that I use for zeolite?
Yeah, because you said that you fitted the force field for the.
Of course, yeah. Thanks for picking that up because I forgot to tell. Of course, for the zeolite, you also need force field parameters. I used something from the literature because there is a force field called trapezio force field. Okay, trapezio force field. So this is basically a force field developed for zeolite structures. So it was these were already in place. Okay, so I took these from the literature. This force field was used by many researchers to model adsorption zeolites. The thing that you may ask, okay, how do we combine these parameters for different atoms? There are mixing rules which we did not talk, but perhaps they were discussed a few weeks ago. When Professor Dorothy, were talking about force fields, okay? I didn't check, but then we have mixing rules. There are different mixing rules, like Lorentz-Berthelot mixing rules. There are geometric mixing rules. There are so many different mixing rules. For this one, we simply use Lorentz-Berthelot mixing rules, which basically is when you have, for sigma, you sum them and then you do, for instance, I mean, we don't need anything between silicon and oxygen, but for instance, if you want to compute interaction between silicon and oxygen, For the sigma, you sum them, which will give you at 5.6, and you divide this by 2, so 2.8, right? For epsilon, it's a bit, you multiply the epsilons and then take a square root, okay, to find the interaction between alike, the two different atoms. So that hopefully answers your question and more.
Yeah, it does. Yeah, I'm also curious, when you simulate like a crystal, the zeolite, like a solid, in the simulation, do you allow it to move, or those are fixed?
For this case, we treated them rigid, because zeolites are, I would say it's a very good assumption to treat them rigid. But there are force fields which allow explicit treatment, flexible treatment of zeolites. Those are, so it also depends on the molecule, whether it's the flexibility is important or not. It also depends on the type of the sorbate, like in this case, 1-bromopropane. For larger molecules, the flexibility tends to be more important. But I would say, this is just, we use the four-site model. So it's not that much important. And also I think this was a screening study. We took into consideration of 237 zeolites, okay? So to do a quick screening, actually, rigidity, treating the zeolite as a rigid structure is justifiable, okay? Particularly for a screening study. And for a small molecule, like 1-bromopropane.
Yeah. Okay. Thank you for the answers.
Yeah, of course. No. Okay. Are there any other questions? I think this will be uploaded to the cloud. The TYC website. There are also some recordings from my colleague Alberto Striola from last year. I didn't cover everything, but you can always check back that material. Unfortunately, I won't be able to upload this paper to TYC because I'm worried that because it's under review right now, they're going to create a problem.
Yeah, the copyright.
Yeah, so I'm going to keep it. But I thought it's okay if I share it with you like this, guys. Well, if you don't have any questions, thank you very much for listening to me. Okay, all the best. Please let me know if you have any questions. Just email me. All right. Again, this is me. Okay, just Google and you'll find my email. Okay, I'm in the chemical engineering department. Okay, thank you so much.